My name is Guan Yu Liu. I'm research scientist at Q-Chem in Pleasanton. It is my great pleasure today to introduce the speaker. This is a very interesting webinar by Professor John Herbert. John received his PhD from the University of Wisconsin-Madison. He then joined Ohio State faculty in 2006 and acquired full professorship in 2014. Along the way, John received numerous honors and awards, too many to mention here. And he has also successfully supervised 12 PhD degrees. John has been board member of Q-Chem since 2012 and is a Q-Chem developer as well. His group contributes state-of-the-art quantum chemistry methods in areas like multi-layer QMM methods, excited states and photochemistry, and many more. He applied these methods into pretty wild systems such as dehydrated electrons, and is also investigating vibronic singlet fission. Last but not least, John was my PhD advisor. I think he did a really awesome job. Here's John.
Okay, thanks, Guan Yu. So I have won many awards, but being able to use GoToMeeting on my own laptop was not one of them. So the technical problems this morning were on my end, but looks like we're running now. So yeah, so as Guan Yu said, I'm going to talk about implicit solvation models, as you can read, for ground and excited states. I want to start off, well, so there's an outline that you can read here. We'll talk about ground state reaction field theory, and then models for computing delta G of solvation, and then non-equilibrium models for spectroscopy, and maybe at the end a brief advertisement for some new stuff, research level stuff on anisotropic models. And this talk is probably going to go about an hour. It's a little bit long, so I hope that you have the patience for that. But I want to start with just a brief overview of the philosophy of this talk. So I just published a fairly lengthy review article on the theory of continuum solvation in quantum chemistry in Wire's CMS. And there's a citation at the bottom, and if you want to read it and can't get it for some reason, feel free to send me an email. This talk is structured basically in the same way as that paper, and like that paper, it's going to focus on the theory rather than the applications of continuum solvation. There are some numbers in this talk, but they're basically where there are numbers, they're intended just to make a point about the theory. And so I'm going to focus on sort of helping you to understand what is and what isn't present at the level of the underlying physics in various implicit solvation models, and to try to dispel what appear to be some fairly common misconceptions based on my reading of the applications literature. And so unlike some of the webinars that my students have given where they spent a lot of time going through QChem input and output files, I honestly found that a little bit too tedious, and I've got an hour's worth of stuff to talk about without that. You know, we have a very detailed manual. We also have a discussion forum. The URL is shown there. I'm fairly active at answering questions on that forum. And so, you know, I think that's a better venue for trading input files back and forth if you encounter problems. Okay, so the first part of this talk, I want to talk about ground state reaction field theory, or in other words, the continuum electrostatics problem, or in the context of quantum chemistry, that gets called the self-consistent reaction field theory problem. So at the heart of it is Poisson's equation, which is shown here. And so given a charge density rho for your solute molecule that comes from Schrödinger's equation, Poisson's equation is what we solve in order to get the polarization of a continuum environment, continuum solvent environment, and we solve Poisson's equation subject to a permittivity function that consists of a sharp interface between the atomistic region representing my molecule that I treat quantum mechanically, and inside that atomistic region, I set the permittivity to 1 because I have explicit Coulomb operators in my Hamiltonian. And then outside that solute cavity, I set it to the dielectric constant of solvent. And so the idea is that I'm going to use glycine for a lot of my examples. That's shown here in some sort of a molecule-shaped cavity. That's also shown over here in green, and what's colored in red and blue is the electrostatic potential generated by that molecule that I solve for at some level of electronic structure theory, and then that electrostatic potential is going to polarize the blue continuum region. And that's the continuum electrostatics problem. That polarization that develops in the continuum then affects the energetics of my quantum mechanical solute, and so I need to include that interaction in my Hamiltonian. And so that sets back a feedback loop, and Schrödinger's equation and Poisson's equation need to be iterated to self-consistency, and that defines the so-called self-consistent reaction field problem. And that's the heart of, but not the end of, implicit solvation. So the workhorse models that you've probably heard of, if you know one thing about implicit solvation in quantum chemistry, are the polarizable continuum models. And so we'll talk about those in a little bit more detail later on. But the basic physical idea is that if I have an interface between two dielectrics, and so in this case, it's a dielectric epsilon for the solvent outside the cavity, and it's a dielectric 1 for the atomistic solute inside the cavity, and that cavity defines a dielectric interface. Maxwell's equations tell me that there will be a buildup of polarization charge at any dielectric interface, and so we can call that a surface charge sigma on the surface of this molecular cavity. And if we neglect any penetration of the solute charge density into the continuum, so we neglect the tails of the wave function that penetrate beyond this cavity, then it turns out that Poisson's equation in three-dimensional space can be recast exactly as a boundary element problem for this surface charge, and that reduces a three-dimensional continuum problem to a two-dimensional problem on the cavity surface that can be solved much more efficiently. And that was really the breakthrough that came from Tomasi's group in Pisa in the early 1980s, and that was the birth of the PCM approach to continuum solvation. And then in practice, that surface charge sigma is going to be discretized into point charges Q that live on the surface of this cavity. Whoops. All right, I'm still figuring out how to run the Frankenstein's monster controllers that we figured out as a workaround for my laptop problems. So in the absence of any outlying charge, and for realistic cavities, there usually is some outlying charge at the level of a couple of tenths of an electron. But in the absence of outlying charge, or in other words, for a classical solute, if my solute were described, say, just by point charges from a force field, the PCM is an exact reformulation of the continuum electrostatics problem. And we demonstrated that numerically some years ago by comparing this so-called integral equation formulation of the PCM, which is this exact reformulation, to the adaptive Poisson-Boltzmann solver, APBS, which is state-of-the-art in classical biomolecular electrostatics. And for a set of classical amino acid solutes, the differences in the solvation energies are less than 1/10 of a kcal per mole, and that error could be, in principle, driven to zero by that's just discretization differences in how these things are discretized. So this really is an exact reformulation of the continuum electrostatics problem. Okay, and now we need to talk about the cavity surface, and physically a very appealing choice for how to define the size and shape of this molecule is to let the molecule define its own size and shape by means of its electron density. And so what's plotted here for my glycine molecule is an isocontour of the electron density, and you can see that it sort of looks like atoms. Turns out that we have iso density contours available as cavity surfaces in QChem, as I'll discuss a little bit more later on. They have some limitations. In particular, there are no gradients for isodensity based cavity surfaces, and so sorry, remember not to press my keyboard controls and to use this PDF controller. And so for that reason, what is done more commonly is to try to approximate this isocontour construction just with a cavity that's formed from a superposition of atom-centered spheres. And so taking the same molecular shape and representing it as atom-centered spheres, we can have a van der Waals surface, which is just the union of some atom-centered spheres with radii RA. For atom A, those radii are usually taken as some set of covalent atomic radii, but then scaled by some empirical factor alpha that accounts in some rough way for the fact that the solvent molecules also have finite size, and so a solvent molecule ought not to be able to approach all the way up to the covalent radius of your solute atom. And a typical value of alpha is about 1.2, but there's a range that have been used. Alternatively, if you had some idea about the size of a solvent molecule, and you could get that from the radial distribution functions for the neat solvent. And so for water, the distance between the first and second peaks in the oxygen-oxygen RDF is about 1.4 angstroms, and so that, so that, I guess it's twice that, and so half that value, 1.4 angstroms, we take to be the size of a roughly spherical water molecule. And so what one can imagine is using a probe sphere like what's shown in orange here and rolling it around the surface of the van der Waals cavity and letting the center of that probe sphere trace out what we call the solvent accessible surface, or the SAS. And effectively, that just means that you've taken your van der Waals surface and you've augmented all of the atomic radii by this probe value. Okay, and so that's another construction that's very simple and available. In the biomolecular literature, there's a lot of talk about what in that literature gets called the Connolly surface. I would say is equivalently known as the solvent excluded surface, and it's shown in pink here, and it basically just tries to smooth out the cusps in this van der Waals cavity that arise anytime you have a seam between atomic spheres. We have a construction of the SES available in QChem if you want to try it, but it doesn't have gradients, and I don't think that the improvements that you get are really worth the hassle. So its gradients are unlikely to be forthcoming. So the two main workhorse constructions are these two van der Waals or SAS that are built from atom-centered spheres. Okay, and then we need to discretize that cavity surface to get a finite set of equations for surface charges. Historically, that's been done by this generating polyhedra or GEPOL algorithm. That's sort of a pain in the mathematics, and so it's not implemented in QChem. What we do instead is to discretize the atomic spheres using Lebedev grids. And so for this chunk of DNA here. I haven't actually plotted the surface. I've just plotted the discretization points. Nevertheless, the contours of the van der Waals cavity are obvious and evident. And this Lebedev discretization has the advantage that the discretization error is completely controllable and can be driven to zero just by increasing the number of points on a sphere. So there are sensible defaults for many things that are chosen, but that number of Lebedev points per atomic sphere can be increased. Defaults are selected so that the discretization error is just less than about a kcal per mole for most things, but that can be driven systematically to zero. Okay, and these cavity parameters, this cavity construction really does matter. In other words, the electrostatic interaction energies with the continuum are very sensitive to the size and shape of this cavity. And to demonstrate that, I've shown electrostatic solvation energies. So G, because the continuum problem really gives you a free energy because the continuum description implicitly averages over the solvent dynamics. So G electrostatics is the solute continuum electrostatic interaction. And looking at that for 2 tautomers of glycine, for some van der Waals cavities that use the same set of radii but different scaling factors, and then for some solvent accessible surfaces. And a scaling factor of 1.2 is sort of what the community has landed on as a rough guess at something workable. And as it turns out, with no tinkering on my part, the energetics that you get from covalent radii times 1.2 are pretty close to those that you get from an isodensity construction, where the community has landed on an isocontour of 10 to the minus 3 atomic units as being a good choice for the size of this water molecule. Interestingly, for the solvent accessible surface, if you actually choose a probe radius that does approximate the physical size of a water molecule, you get some energetics that are really not plausible here. And in fact, to get plausible energetics, you need to use a probe radius that's considerably smaller than the physical size of a water molecule. And that's something that's been known in the classical biomolecular electrostatics literature for some time. Okay, and then finally, this is kind of an old story, but the discretization approach that's available in Q-Chem is designed to intrinsically yield smooth and continuous potential surfaces, despite the fact that there are grids involved. And so it's smooth enough to use it for energy conserving molecular dynamics in continuum solvent. And so if we look at the tautomerization between the proton transfer reaction between these 2 tautomers of glycine, these 2 tautomers have very different electrostatic solvation energies. But if sorry about this. Every time I press the down arrow on my keyboard, it takes me back to the beginning, apparently. If I blow up the region where the proton transfers, you can see that the solvation energy does change dramatically, but it does so in a completely smooth manner. So that smooth discretization, my group designed it for PCMs, but then the Q-Chem staff has later extended it to the SMX models that I'm going to talk about in the second part of this talk. Okay, so I want to talk a little bit before I get to those models about connections between different PCMs. So I just told you a few minutes ago that the so-called integral equation formulation, IEF PCM, was originally derived as an exact reformulation of Poisson's equation in the absence of outlying charge. Dan Chipman came along not too much after that in the late 1990s and recognized that for a quantum mechanical solute, there is always charge penetration, there's always outlying charge. And so can we build that in from the beginning and derive a continuum electrostatics approach that takes account of the so-called volume polarization that comes from the the additional polarization from the tails of the quantum mechanical charge that penetrate into the continuum. And the answer is, not only can you derive a continuum formalism that takes that into account, but it turns out to be the same. And so he called this method SSVPE, for surface and simulation of volume polarization in electrostatics. But operationally, it obeys the same equations as IEF PCM, but I would say it puts IEF PCM in a much more useful perspective, that IEF PCM is exact for all of the charge that's contained inside of your cavity, but also contains an approximate correction for the tails that penetrate out into the dielectric medium. And the other thing that Chipman's derivation makes manifest that was not clear in the original formulation of these models is that the so-called conductor-like model, cpcm, emerges rigorously as the high dielectric limit of this more exact formulation. And so just to show you some numerical data for a particular solute, comparing the electrostatic solvation energies that we get with IEF PCM versus the conductor-like model cpcm, you see that those two things converge in the high dielectric limit, and honestly, epsilon greater than 10 might as well be the high dielectric limit. So there's some differences that you can see in nonpolar solutes, but even those are fairly small. And so that brings us to, so I guess there's one slide in here about different flavors of PCM, and I'm not going to go through the mathematics here, but all of these models can be cast in a sort of similar looking equation for the surface charges Q, but with different matrices. What is immediately evident from this sort of complicated table is that the conductor-like model is just mathematically much simpler. And then the other thing to note is that this D-dagger matrix that shows up only in SSVPE turns out to be a little challenging to discretize for cavities that have sharp cusps, like the van der Waals cavity. And so it's actually better in those cases to use IEF PCM, which is exact in the limit of a continuous surface charge, but is a little different in the way that it's discretized. But sort of a deeper question that addresses a misconception that I see all the time in the continuum solvation literature is, what is the difference between cpcm, the conductor-like model that I've just introduced as the high dielectric limit of a more exact formulation of the continuum electrostatics problem? What is the difference between that and the so-called conductor-like screening model, Cosmo, that was introduced by Andreas Klampt in the early 90s? The answer is that both of these models fundamentally solve the same equation for the surface charge. So if you go back to this more complicated mathematical slide, let's see, SQ equals some scaling factor times V, which is the electrostatic potential, is my basic equation. And that comes from the equations for the case where the medium is an actual conductor, is epsilon equals infinity, and then rescaled in some way to account for the fact that your actual solvent has a finite dielectric constant. And historically, and then that scaling factor is re-expressed here in terms of a parameter zeta. And in the early days, people took zeta equals 0, and that was suggested by the form of Gauss's law that says that I can relate the total surface charge, so the integral of sigma over the cavity surface, can be related to the charge that's inside by this dielectric factor, and so we rescale based on that factor. This is also the same factor that shows up in the Born-Ion model. And then a little later on, it was recognized that, well, oftentimes your solute is charge neutral, and then the leading order multipolar term is not a Born-Ion, it's an Onsager dipole in a cavity, and zeta equals 1/2 gives you the right leading order form for Onsager's model of a dipole in a spherical cavity in continuum. And so there's a few different choices, but differs only in the rescaling of this electrostatic potential. But I would argue that the method that solves the equation in the box ought to be called cpcm, because Andreas Klompt takes an additional step in Cosmo where he actually uses 2 different cavities in his solution of these equations. And so he first solves the conductor-like cpcm equation on a solvent accessible cavity, a larger cavity augmented by a probe radius, and then he projects those charges inwards onto a van der Waals cavity to evaluate the energy. And so that model is available. It has long been claimed by Klompt that second step, the projection inwards onto a smaller cavity, is important for correcting for the outlying charge. And I would say 2 things to that. First of all, he has shown that with 2 different choices for this zeta parameter, zeta equals 0 for ions, zeta equals 1/2 for neutrals, that actually his Cosmo model gives really good agreement with IEF PCM, even in low dielectric solvents. So not just in the epsilon goes to infinity limit. But it's a little funny, because now that we understand that cpcm really is the high dielectric limit to SSVPE, we know, or you would know if you went through the details of this derivation, that SSVPE contains a correction, even in a single cavity implementation, contains a correction for the outlying charge. And so it almost feels like we're correcting for that effect twice in Cosmo. But the results are what they are. Let me show you some numerical results that come from Chipman's papers for 4 different molecules and ions in a high dielectric and a low dielectric solvent. There's a set of exact numbers here that come from solution of Poisson's equation in 3-dimensional space, including all of the outlying charge. But you can see that Chipman's SSVPE model is essentially exact to sort of tenths of kcal per mole level of accuracy. But if I look at this conductor-like model with zeta equals 0 for the ions and zeta equals 1/2 for the neutrals, it is almost exact itself, even in a low dielectric solvent like toluene. And so, and the cpcm really is a much simpler cavity construction. Unlike the isodensity, cpcm really is a much simpler model than IEF PCM. Okay, so just to close this section of the talk on ground state reaction field theory, with some recommendations and or at least some caveats, I would say that there's very little difference between the conductor-like model and more exact things, really even in nonpolar solvents, but certainly by the time you get to epsilon equals 10, which is sort of ketones, so moderately polar organic solvents have epsilon equals 10. By the time you get to acetonitrile, you're all the way up to epsilon equals 35 or 37, something like that. So there's operationally very little difference, and cpcm is much easier. It's also much easier on the developers, and for that reason, cpcm has both analytic gradients and Hessians, whereas IEF PCM has only gradients. At least if you're using a construction that's just based on atomic spheres, so van der Waals or SAS cavities. Fully self-consistent at the SCF level, you can do correlated wave function things just by putting the correlation on top of molecular orbitals that are polarized from the ground state self-consistent reaction field problem. And so that allows you to get energetics at the correlated level of theory. We don't yet have gradients for, say, MP2 plus PCM, although those wouldn't be too hard to implement customers complained enough. Let's see, the SSV-PE model also has an isodensity implementation in QChem that does not have gradients, and that's not just a QChem problem. Actually, no one has figured out how to write down an analytic gradient for an isodensity cavity construction that can be tractably solved, and I doubt that that is forthcoming. But for energetic purposes, I really like this isodensity cavity implementation because it's basically a one parameter cavity construction, and that one parameter, which is the ISO value, feels very directly connected to the physics. And so, you know, sort of for spot checking certain results, I like having that model available. And then something that I'm going to start to get into in the next part of this talk is that this continuum electrostatics problem alone is not enough for solvation energies. So we need non-electrostatic terms. But before I do that, I do want to spend 1 or 2 slides looking at some QChem outputs, just to sort of familiarize you with what you're going to see. If I do some level of SCF theory with solvent method equals PCM, I get cpcm by default with the van der Waals cavity with the radii scaled by 1.2, although all of those things are configurable. So what you're looking at here is the end of the SCF cycles, and then there's a printout about the PCM, and this is actually the Zwitter ionic tautomer of glycine, so the electrostatic solvation energy is about -48 kcals per mole. And the way it gets printed here, highlighted in red, is that the SCF plus PCM problem minimizes an energy functional that consists of the vacuum part. So that's expectation value of your vacuum Hamiltonian, or if it's DFT, that's your vacuum density functional, plus an electrostatic solvation energy that can be written as the expectation value of a reaction field operator that generates the electrostatic potential. There's a factor of 1/2 that you lose to the work of polarizing the continuum, and so this entire term is what I've called G electrostatic, but for this reason it sometimes gets called V/2, electrostatic interaction energy over 2, and so in the code this gets printed as H0 plus V/2. And then you see a space here highlighted in blue for a bunch of other contributions, non-electrostatic contributions to the energy, including cavitation, dispersion, repulsion. And so there are functional forms that have been available in the literature for decades for how you might parameterize these things. There are not really widely available parameter sets, and so we coded this up so that you could experiment with it if you like, but it's not in there by default, which is why all of these numbers are 0. And so by default, what you get is an electrostatics calculation only. And I would say that when you use the term PCM, that really refers to the electrostatics part of the solvation problem, the part that comes from Poisson's equation. And that is not enough to compute a free energy of solvation. You need a bunch of other stuff that we just collectively call the non-electrostatic parts of the solvation energy. And that's what I want to talk about next, is models for how we would compute a delta G. And let me first show you some numbers to tell you that just to quantify the fact that an electrostatics only approach is not an appropriate method for computing solvation energies. You have no idea how many things I see in the literature comparing their new solvation model against PCM. If you go and look at error statistics for an electrostatics only PCM, and this is using the Minnesota database of solvation energies compiled by Chris Kramer and Don Trular, and these are mean unsigned errors, and these numbers in orange are quite large, especially for ions. So 7, 8, 12 kcal per mole mean errors for ions. And so that is really the state of the art in electrostatics only, and it's not good enough to be predictive for free energies of solvation. Whereas if you take the SMD model that I'll talk about in a little bit, but what it does is it takes cpcm electrostatics but adds a non-electrostatics term, and so it's the appropriate thing to compare to the cpcm electrostatics only, and you see that these green numbers are significantly improved, and maybe you like these errors, maybe you don't, but this is almost state of the art. And so it's sort of this is what you can do, and it's obviously better than these electrostatics only numbers. Okay, and so the state of the art for many years in continuum solvation and quantum chemistry has been these so-called SMX models of the Minnesota group, Kramer and Trular, SM standing for solvent model, and then in QChem, the X is either 8, 12, or D for density. And the idea is that the total free energy of this molecule has some parts in black that we've seen, internal energy, electrostatic solvation, but then it's got everything else, and non-electrostatics is what we call the everything else. And so these SMX models are an attempt to augment continuum electrostatics with some non-electrostatics parts, and that non-electrostatics part is not broken down in a physical way like I've written it here, cavitation, dispersion, hydrogen bonding, etc. But it's parameterized using an ansatz of solvent exposed surface areas of the atoms. So the SAK here is the surface area of atom K that's exposed to the continuum, and then there's a parameter that has dimensions of surface tension. Actually, if you dig into this further, the gamma parameters are further defined in terms of another set of parameters for pairs of atoms. So there's as many as so there's actually a greater number of parameters than the number of atom types, and I'm not going to get into the parameterization at all. But the idea is that the idea of Kramer and Trular, and they called this a universal approach to solvation modeling. And it's universal in the sense that they've done this for a very large number of solvents, 170 some that are available in QChem, and the idea is that Kramer and Trular will claim that electrostatics and non-electrostatic interactions cannot be separated in a model-free way, and so they don't try. And so the electrostatics term gets parameterized alongside the non-electrostatics term for any of these SMX models. And so in particular, that means that for an SMX model, those atomic radii are not covalent radii that you look up in your general chemistry textbook. They are parameters of the model, okay, and not intended to be adjustable. So this is all parameterized together, and just to show you one output file of how this looks, again, end of the so this is for solvent method equals SMD, end of the SCF iterations. In this SMD output, the H naught and the G electrostatics gets added together, and Kramer and Trular call H naught the electrons and nuclei part, and then some people call electrostatics polarization. I think those are synonymous, but together you get this electrons and nuclei and polarization, or ENP. And then the non-electrostatics part that comes from that exposed surface area ansatz is this blue number, 4.6 kcals per mole. It happens to be repulsive in this case, and then the sum of all of those things is the total free energy. It turns out that, and I sort of just noticed this in the course of putting this talk together, that the the way that the output looks for SM8 is a little bit different in that the internal energy and the electrostatics get broken out separately for whatever reasons. But okay, but let's look at how they perform. So this is on the same data set that I used to show you some error statistics before, but now I'm focusing just on the hydration energies and showing you the 3 different SMX models that are available in QChem, SM8, SM12, and SMD. And you know, the errors are what they are. I would say that there's not too much difference in terms of these error statistics between these models, that not too much difference that's statistically significant. Maybe this 6 kcals per mole is statistically larger than these 4 kcals per mole, but the performance of these 3 models for delta G's is really quite comparable, and so the choice between them is dictated by certain other considerations in QChem that I'll get to in a minute. But I do want to highlight this last column of numbers. So this is a model designed by Dan Chipman, and he calls this the very generic name of the composite model for implicit representation of solvent. And so what this does is combines his isodensity SSVPE for electrostatics, and then tries to combine that with some physically motivated functional forms for the non-electrostatics part. And so the idea here is that he's trying to build something approaching a first principles model for implicit solvation, and in particular he actually is explicitly trying to separate electrostatics from non-electrostatics in a model-free way. And throughout his paper, he sort of implicitly makes the case that an isodensity cavity is really the only hope that you have to be able to separate electrostatics and non-electrostatics in a model-free way. And so he does that, and he combines SSVPE electrostatics with some physically motivated functional forms for dispersion, repulsion, and hydrogen bonding that have relatively small numbers of parameters. So only 5 parameters for Protic solvents and 2 parameters for a solvent that doesn't hydrogen bond. And yet, you can see that the error statistics are actually slightly better than any of these SMX models. And in particular, the experimental errors for the delta G's of solvation of ions are several kcals per mole, and I would say that that these numbers have really reached the limit of the experimental data. I don't think it's possible to reduce these errors any further in a statistically meaningful way. And so that's the good news. That the downside of this CM-IRS model, I mean, that really feels much more physical than any other model for delta G's, performs better than any other model for delta G's, however, is only parameterized in 5 solvents, and honestly, we could probably parameterize it in more solvents. I think that would work. The real limitation is that with an isodensity cavity construction, you don't have a gradient, and that's sort of why my group has not been rushing to reparameterize this for a bunch more solvents. Let's see, these are a couple of screen captures from the QChem manual, so I'm not going to walk you through these because they're in the manual, but just to inform you or remind you that there are some tables at the beginning of the section in the manual on implicit solvation that summarize all of the available models, what the cavity constructions are, and whether or not there are gradients available. Okay, so just to wrap up this part and review a little bit, PCMs are electrostatics only models, and that means that they are fundamentally inappropriate for computing delta G of solvation, or at least they need to be augmented by non-electrostatics currents in order to compute delta G's of reaction. That doesn't mean that they're not useful. In fact, the PCMs are very useful for spectroscopy, and that's where I'm going next. And the way that I think about PCM is that it provides improved boundary conditions for a solution phase quantum chemistry calculation. So it provides boundary conditions to in particular to say how the frontier energy levels of the orbitals are adjusted by the presence of a continuum, and how those frontier energy levels are adjusted is obviously very important to the solution phase spectroscopy. Okay, and we have this available in a fully self-consistent form at the SCF level, and then you can do post-SCF calculations, correlated wave function calculations, using solvent polarized, PCM polarized MOs, and that's sort of a 0th order correction to the solvation effect. There, doesn't explicitly try to do the 0th order at the level of the solvent effects, although I think there's very little reason to go beyond that. If you do want delta G, though, you need a model that contains non-electrostatic interactions, and the models that do that and also have gradients in QChem are SM8 and SMD. Because of the way that electrostatics is parameterized in SM8, it is fundamentally limited to a few small basis sets. That's a limitation of the model, not a limitation of the software. SMD, on the other hand, uses PCM electrostatics and is available in arbitrary basis sets. And then once again, despite the fact that it doesn't have a gradient, I really like the idea of having an implicit solvation model that's based on an isodensity cavity construction. That if I have any doubts about anything, that's my fallback. And in particular, the CMIRS model and the isodensity SSVPE that underlies it accounts in an automated physical way for the fact that certain atomic radii might change in the course of a chemical reaction, especially, for example, if you were doing redox chemistry where you're changing the oxidation state of some atom, maybe a transition metal or something, then you might expect that the size of that atom changes as its oxidation state changes. Okay, so the last major part of this talk is to talk about spectroscopy, and particular electronic spectroscopy, and how, basically the question is, what should be the response of a continuum solvent to an electronic excitation of my solute, or considered in the same way an excitation or even an ionization. Done a lot of work in my group on photoelectron spectroscopy, and that can be treated within the same formalism. So the basic idea, what you need to know about electrostatics that's new for the excited state problem, is that in reality the permittivity of a dielectric material is a frequency dependent function, and it's in general complex value. Although it's real valued in the two limits that we're going to use, and those are the zero frequency limit. So the zero frequency limit of this permittivity is the static permittivity, or that is just the bulk dielectric constant. And then the other limit that becomes important for spectroscopic applications is the infinite frequency limit. And for historical reasons, that gets called the optical dielectric constant, or the optical permittivity. And you can actually look at this table of different common solvents that has both the static and the optical dielectric constants. And for basically all common solvents, the optical dielectric constant is 2, plus or minus about 0.2. And that has to do with the fact that common solvents are insulators, and to get a larger value of epsilon infinity, you would really need very low-lying electronic states. But the basic idea here is that we're going to polarize the ground state using the static dielectric constant epsilon naught, the zero frequency dielectric constant. And then we're going to excite, and that optical dielectric constant is describing that part of the permittivity that comes from the electrons. And even for a vertical excitation, the electrons on the implicit solvent ought to be able to respond, even if the nuclei are frozen. So we freeze out in a vertical process the orientational polarization, but we should allow the electronic polarization. And interestingly, you see something like water that's a high dielectric solvent, epsilon naught equals 78, but the optical dielectric constant is almost the same as in these nonpolar solvents. And you know, there are reasons for that we could discuss, but the main reason that water is a high dielectric solvent is because the individual H2O molecules have large dipole moments, and if they are allowed to reorient, they can screen charge very effectively. But if you lock that out in a vertical excitation process, the solvent's ability to screen charge drops dramatically to epsilon equals 1.8. Okay, and this slide basically says the same thing, and I think I'm not going to go through it, but basically it says the philosophy here is, well, maybe I'll go through the three-step procedure here at the bottom. The philosophy is that we do a so-called equilibrium PCM calculation where we solvate the ground state using the static dielectric constant, but then we separate that polarization into so-called fast and slow components, or equivalently electronic and orientational components. And the orientational component we're going to freeze at the ground state value for, but for a vertical excitation process, the fast or the electronic part we're going to repolarize in the excited state, not using epsilon 0, but using epsilon infinity. So that's the basic phenomenology. And I want to illustrate how it works, or that it does work, not using electronic excitation, but actually using vertical ionization energies. So this is from some of my own work on solution phase photoelectron spectroscopy. And the way that we have done these calculations is really to use PCM as boundary conditions on a QM region that contains the solute of interest, which is actually this orange or gold ball here, and about 2 solvation shells of explicit water. And so for some very simple solutes here, where there are experimental aqueous phase photoelectron spectra, we can compare the results of a non-equilibrium PCM versus an equilibrium PCM that didn't take any account of epsilon infinity at all and just polarizes everything using epsilon naught, or what we expect to be a poor approximation is vacuum boundary conditions. And what you can see if you peruse these numbers is that the non-equilibrium PCM numbers are in pretty reasonable agreement with experiment. There's some issue for lithium here that I think is intrinsic to the MP2 description of the electronic structure, but the equilibrium PCM are in less good agreement, especially for the anions, and that's not an accident. It's because for those anions, when you photodetach an electron, you go from a strongly solvated anion to a much less strongly solvated neutral radical, and the equilibrium PCM really can't handle that, but the non-equilibrium formalism can. The other thing that this setup is useful for is being able to get converged ionization energies with a relatively modest number of explicit solvent. So it is known in this field that if you want to compute ionization energies for an aqueous phase solute, and you want to do that with respect to increasing numbers of explicit solvent molecules, that those calculations are very slow to converge with respect to the number of explicit solvent molecules. It takes you hundreds of water molecules. And if photoelectron spectroscopy is not your thing, think about pKa's, because that's maybe a more mainstream chemical application, but where you're changing the charge state of your solute either by adding or removing a proton, H+, and pKa's are also notoriously slow to converge with respect to explicit water, unless you slap continuum boundary conditions around the whole thing, and in particular non-equilibrium continuum boundary conditions. And then looking at these data, these are for nitrate ion, even though I forgot to label it, with in a gas phase calculation with respect to increasing the number of explicit water molecules is very slowly convergent, and we sort of ran out of gas before we bothered to converge this red curve. But with non-equilibrium continuum boundary conditions, this blue curve converges quite nicely to the experimental value by maybe, say, 35 explicit water molecules, which is about 2 solvation shells. So this is a very and now when you do that, you are obligated then to sample over all of the solute degrees of freedom. And so it really you sacrifice some of the simplicity of a continuum approach where all of the averaging is implicit in the dielectric constant. Now you have to do your own averaging over the explicit waters, but on the other hand, things converge to the right answer relatively quickly. Okay, so let me return to electronic excitation energies, and based on the phenomenological description that I introduced, where we polarize in the ground state using epsilon naught, and then we repolarize the fast part of the solvent response in the excited state, you could write down a Schrödinger equation that corresponded to that phenomenology, and it would have the vacuum Hamiltonian, and then there would be a slow ground state reaction field operator and a fast reaction field operator. So this is the epsilon naught, this is the epsilon infinity, but for state K. And so that is sort of phenomenologically straightforward, but it's numerically challenging because the Hamiltonian here now depends on its own wave functions. And so this is a so-called state-specific Hamiltonian, and this eigenvalue problem becomes very hard to solve in the presence of degeneracies, and even if that's not an issue, your eigenstates are eigenstates of different Hamiltonians, and so they're not mutually orthogonal, and that means that excited state properties are not really well defined. And so for those reasons, we try to avoid solving this state-specific eigenvalue problem, and we can avoid solving that by perturbation theory that works pretty well. And so the idea is we're going to take as our H naught, our 0th order Hamiltonian for perturbation theory, we're going to take the ground state reaction field Hamiltonian. So letting both the slow and the fast parts of the reaction field be described with epsilon naught. Okay, so this is really the same as the standard PCM Hamiltonian for the ground state problem that I talked about before. And then the difference between this Hamiltonian and the one that we really want is just the difference in the fast part of the polarization between the ground state and the excited state. And we treat that as a perturbation using first order perturbation theory. And this happens to be equivalent for TDDFT to something that has a very confusing name in the literature, so maybe I won't say it out loud and confuse you. But we could look at how this performs for solvatochromatic shifts, and these are calculations that I did with Andreas Droiv's group a few years ago. His group is very into this algebraic diagrammatic construction at second order, so this is a correlated wave function treatment, more or less excited state MP2 plus a cpcm, and there's a bunch of numbers here that are sort of even, this graph is kind of makes my eyes blurry, but there's a bunch of different derivatives of nitrobenzene, each in 2 or 3 different solvents, and there are experimental data for all of these, and the take-home message is that all the bars are basically the same height, which means that we're getting good agreement with experiment for the solvatochromatic shifts and it doesn't matter too much how self-consistently we treat the electron correlation with the SCRF problem. Basically, we can solve the SCRF problem at the level and then put correlation on top of it in one shot, and that works perfectly well and is pretty easy. Okay, there's one not so easy bit that we have to push through, and then we can look at pictures for the rest of the talk. And that's this so-called linear response approach to excitation energies. So in gas phase quantum chemistry, I think most people are more familiar with Schrödinger type approaches to compute excited states, but there is a parallel linear response formalism where Green's function formalism, where you compute the excitation energies as poles of the response of your ground state density or ground state wave function. And in the gas phase, those two theories are essentially equivalent. That is not true in continuum, and this was sort of a mystery for a while that was eventually solved by Kami's group or the PISA group by in these papers that are cited at the bottom. I'm just going to quote the result for the non-equilibrium linear response excitation energy, h bar omega, for excitation from 0 to state k. So there's a 0th order part, and that 0th order part means what does the quantum chemistry tell you in the presence of the ground state reaction field? So the parenthesis 0 means ground state reaction field. What's the excitation energy for state k? And then everything else is what's the solvent continuum correction to that excitation energy. And this operator V generates electrostatic potential, but it shows up in linear response theory between two different states. And so basically that looks like a transition moment. And so the linear response approach to continuum excitation energies has a funny feature that the solvent correction goes like oscillator strength. And that means if you have a transition that's spectroscopically dark, you get basically no solvent correction, and that doesn't feel right. Although there are people that have argued that this looks like a correction for the differential dispersion between ground and excited state. But anyway, in contrast, we very much prefer the Schrödinger eigenvalue approach, which is fundamentally state specific, but can be well approximated with perturbation theory. And one reason we prefer that is if you consider the case of a charge transfer excitation, where you move basically a full electron between donor and acceptor orbitals that basically have vanishing overlap. The transition dipole, if it really does have vanishing overlap, the transition dipole is going to be pretty close to 0, and that means that the linear response formalism is going to give you very little solvent correction for something that looks like a charge transfer state, potentially in a polar solvent, and that feels like something that should actually have a very large solvent correction, and the state-specific approach will give you that, and through the math that's shown here. But the difference is that the delta reaction field for the linear response goes like transition dipole mu 0k. The delta reaction field for state-specific goes like delta density. So this charge transfer state definitely has a large delta rho, and the state-specific formalism can then give you a large solvent correction in a polar solvent. Okay, and I'll show you one example of how the inputs and outputs look for TDDFT. So the way to think about TDDFT in this case is to think about it as an eigenvalue problem in the space of single excitations. So think about it as the correlated analog of CI singles. And so there's a state-specific Schrödinger equation that we could write down for CI singles that's going to be a pain to solve. And so we take a perturbative approximation. And that's the calculation I'm actually going to do. Here's an input file. I haven't shown you the molecule, but doesn't really matter, but there's a CIS relaxed density keyword that's optional, although and to compute relaxed densities incurs a cost that's on the order of the TDDFT gradient cost. Basically, is the TDDFT gradient cost. But on the other hand, the unrelaxed density is not really the true excited state density. So if you really want to be using the actual TDDFT excited state density, you need to specify that. Then there's some keywords in the $PCM section to invoke this non-equilibrium state-specific theory. I haven't actually specified what the PCM model is because it defaults to cpcm, which I think I wrote on the next slide. Right, okay. Defaults to cpcm with a van der Waals cavity radii scale by 1.2. There's some output that's now extends onto the next slide. And so if I just look at one particular state of this molecule, the way that this comes out is that the non-equilibrium excitation energy, 0 to state K, comes out as a 0th order excitation energy. And that's the, what does the quantum chemistry tell you in the presence of the ground state, of the ground state reaction field? That's the 0th order approximation. And then the non-equilibrium corrections, and there are separate corrections for state specific treated perturbatively, or linear response treated perturbatively. And I think that's actually fairly readable in the output file. It's an embarrassing typo that I pointed out to my student last night. Okay, and so I realized I told you this was going to go an hour. So thank you for your patience, in those of you who are still around. But I'm going to just show you one last thing at the level of one slide worth of pictures. I guess the first picture is an equation, but this is something that my group has been working on for a few years now that I think is kind of fun, and it's how do we treat anisotropic solvation environments within a continuum formalism. So most continuum formalisms are designed for bulk isotropic solvation, isotropic solvation in bulk water. There are some formulations that are modified to take a tensor valued dielectric function like you might have in a liquid crystal. I'm not that interested in liquid crystals. I'm interested in things that are really genuinely anisotropic because they have an interface, for example, so an air-water interface. And so the idea is that Poisson's equation still works, sometimes called the generalized Poisson's equation in this context, but if we can cook up a permittivity function that will represent this interface, then we can solve Poisson's equation. And it's a little slower. We're working on that because it doesn't have a two-dimensional PCM type formalism, but you can do some interesting some interface problems. With the collaborator, we've also looked at coumarin dyes in capsules where there's some reason to believe that the dielectric constant that the dye experiences inside of this capsule is significantly different than the dielectric constant of the aqueous solvent, and so we can model that. And so that's available. It's still kind of a research level. I mean, it's in the release version of Q-Chem. It's still sort of a research level code, but I just wanted to advertise. And with that, I'm not going to try to summarize. This is going to be recorded on the internets for all posterity, so you can back up and rewind if you need the summary. So I'm just going to close by thanking all of the people that have done this work. So the ones whose pictures are shown are the students in my group that worked on this. Quan Yu told you at the beginning he was my student, but he did some other very nice work with me that was unrelated to continuum solvent. We've also I've hosted students and postdocs from a few other groups to collaborate on some things. This one with Paul Zimmerman's group is still ongoing at the moment. There's a review article that summarizes a lot of this stuff, and if you have difficulties, I'm happy to have specific conversations about QChem input files. I'm not dodging that. I'm just saying that I think there's a better forum for that, and it's the QChem Talk forum. So that's it, and I'm, thank you for indulging me for this lengthy talk, and I'm happy to take some questions.
Thank you, John. This is a really interesting and informative presentation. We got several questions. So first one, so in the QChem, the SMD model use cpcm by default. Is it recommended to run on IF PCM for SMD as the original paper suggests?
So the original paper, the original paper does suggest IEF PCM. However, the original paper also, Kuan-Yu, do I still have the meeting controls?
Yep, you have the control.
Okay, I'm attempting to change the slide number here. Okay, maybe.
I guess when I was scrolling through the questions, kind of interfere your control.
Let's see. I'm just trying to back up to that slide. Let me just put the relevant data on the screen. It's a good question, by the way, but I think the answer is that it's fine to use cpcm, because if you can see these gray numbers, this is the original version that used IEF PCM electrostatics, and at the level of these error statistics, these are identical, right? And furthermore, I got both of these actually all of these numbers, maybe not the orange ones, but the green ones and the gray ones both come from the Kramer and Trular papers, right? So these are their numbers, and they're telling you that it's basically identical. And so, they did in the end, I think, recommend IEF PCM for largely, and in the very first implementation in QChem, I think that's how it was set up by default. It has now changed because it turns out that cpcm really is simpler from all angles, and in particular simpler on the programmer. And so I think that that's the reason that the default version of SMD in QChem is now switched to cpcm. But looking at these, and I think that's important to be aware of, but it doesn't feel like it's a major change to me.
Thanks. So next questions, new to the field, but I was wondering how big can the system be, and can they contain counter ions? For example, would PCM work well for a small scale aggregate with about 100 molecules surrounded by water and counter ions?
Depends on how big your molecules are, right? So, what 100 molecules or 100 atoms? Does it say?
It's set molecules.
Okay, so let me just answer sort of in general terms. I mean, for something large, you're going to be doing SCF theory, right? So you're presumably going to be using density functional theory, and fundamentally the cost is going to be limited by your density functional theory cost so how much stuff are you going to put in the atomistic QM region. And so if you if you try that out and with whatever your preferred density functional and basis set is, and see what the cost of that is, that fundamentally is the limiting factor. And as far as the cost of solving the, say, the PCM, the continuum electrostatics equations, if you're using a PCM, and so that includes using SMD that's based on PCM electrostatics. I've written about this. I decided not to discuss it in this talk, but fundamentally, you have a set of linear equations that in the discretization parts, and so fundamentally, the solution of the PCM equations goes like number of grid points cubed, and so that can become a problem. However, we implemented some linear scaling solvers for large systems, and those get kicked on automatically at some system size that was someone's best estimate of when that was a good idea. You can always turn them on yourself, and so fundamentally there's a big set of linear equations that you may not want to solve by diagonalization, but it should be solvable. And so I really think that the size is limited by the DFT size. And so can you do however many 100 molecules, and can you put explicit counterions? I mean, the answer to that is yes. You can put whatever you want in the explicit atomistic region, and then whether or not you can afford to do that calculation really comes down to can you afford to do the atomistic QM part. And then I think that the continuum solvers, you might have to change a couple of variables in your $PCM section to turn on some of these linear scaling things. But I think fundamentally, if you can afford the DFT, we can make the PCM work. That's the short answer.
Thank you. So next question, can PTSS be used to compute emission energies and solvent?
Yes.
Okay.
There's an example in the manual. I know that there's a bug ticket right now that says that may or may not have been resolved, that says that the manual example is confusing, and I as part of this project, I used the putting together of this webinar as an excuse to go back and look at some of that, and I'm going to go back and look at how this stuff gets written up in the manual. But I had sort of intended to look at that emission example and put it in this talk, but it in the end it just didn't make the final draft. But there's an example in the manual. If the example causes you problems, please bring it to my attention through the talk forum.
Okay. Thanks. Next one, how does the explicit solvent model compare to the PCM with two salvation shells for vertical ionization energy?
Oh, okay. How does explicit solvent? So I think, well, my hand waving guess. Again, sorry. Controls are going to take me a while to get to the data that I want. My hand waving guess is that they converge to the same thing. However, my intuitive guess, because we haven't actually done that calculation, but it's pretty clear that these numbers are converging. So this, again, I went through this a little fast, and I didn't label the fact that this is NO3 minus in some amount of explicit water, and just looking at the vertical ionization energy, and the green and the blue are equilibrium and non-equilibrium PCM, and there the convergence is fast enough that I think you can see it with your eye to convince yourself that it is converging. And somehow the limit as we go to infinity towards the right is that explicit calculation that the person is asking about, because we do sample over all. There's an MD simulation that underlies this, and so we are sampling over all of the explicit waters, and so the far right limit of this graph is that explicit solvent calculation. And so even though we haven't actually done exactly that, I'm pretty confident in saying that it's going to converge to the same value. In principle, this is the calculation that the person is asking about, where we use the red one, where we use no continuum boundary conditions at all. We just run an MD simulation. So the simulations in this example are all classical MD with a polarizable force field done outside of Q-Chem. But then we come in and we do electronic structure calculations on clusters and sample over snapshots. And here, those clusters have vacuum boundary conditions. And this is probably converging, but it's clear that it's going really slowly. And there's, I don't know, we cite half a dozen other papers in this preprint of people who have done these calculations in explicit solvent without any kind of continuum boundary conditions, and they claim, depending on which paper, anywhere from 3 to 500 or more water molecules are required, and the limit here is 70. So I think the answer is it would converge, even if we haven't exactly done that calculation to test it, but these data strongly suggest that it would converge to the same answer.
Thank you. So next one, thanks for the very interesting presentation. Would it be possible to use any off-the-shelf continent models for solvent mixtures with arbitrary dielectric constants?
Right. So I vaguely remember that in the chemical engineering literature, what they basically do in those cases is to just take the weighted average of the dielectric constant. So if you've got a 60-40 mole fraction of A plus B, then you would take 0.6 times the dielectric constant of A plus 0.4 times the dielectric constant of B, or maybe they use a geometric average. So this is something that people have done in the chemical engineering thermodynamics literature, I mean, that's a calculation that you would then do on the back of an envelope and just dial in the dielectric constant that you wanted. The probably more the more challenging part of a solvent mixture is presumably the non-electrostatics parts, and so that's a super crude way to do the electrostatics, but it's maybe not that incongruous with just the fact that electrostatics alone is a fairly crude approximation. How you do the non-electrostatics part is a lot more challenging, and I'm not sure that there is an off-the-shelf model, at least not one that's available in Q-Chem for doing the non-electrostatics of mixtures.
Yeah. Thank you. So next one we have for emission spectrum calculations, should one use the static permittivity for the excited states and the optical one for the ground state?
Exactly. So in an emission, you're in. So if I were being careful in a general discussion of this non-equilibrium formalism, I would have just said initial state and final state rather than ground state and an excited state. And if you do that, if you all of my zeros in that part of the talk, if you just consider 0 to be the initial state and k to be the final state, then it's the same formalism, right? And for an emission, you would probably want to start from the geometry of the excited state. So the first thing that you would probably want to do is to optimize the, if this is, say, I don't know, S1 to S0 emission, you optimize the geometry in S1 and take the minimum energy geometry in the excited state to be your initial state, and use the static dielectric constant for whatever your solvent is, and then the final state becomes the ground state, and that is we did implement that. My postdoc Zichang, that was one of the things that he did for sure, and it's my former postdoc anyway, and it's in the there is an example in the manual. Like I said, someone, I think Felix Placer was having some problems with that recently, and I am intending to look into it to see if there's really an issue, or if it's just that things aren't described well enough in the manual. Probably the manual can always be improved, and so I was intending to use this talk as an excuse to make a pass through all of the continuum stuff in the manual and get that cleaned up.
Thank you. So, next one, in the PEqS approach, how to consider the optical dielectric constant as it contains to dielectric region for water-air interface?
Oh, so that's a really subtle point, and it actually cancels out. If you, it turns out we're right on the right slide. So if you go look at this Koons and Herbert paper, JCP 2018. So this is where that's the paper that discusses this Poisson Equation Solver for the anisotropic dielectrics, and it also takes the non-equilibrium continuum formalism that we had originally developed for excitation energies, and also originally developed for PCMs, and it ports it to both anisotropic dielectrics, and I guess we had already done it for ionization energies with PCM, but what I looked at with Mark Koons is ionization energies in anisotropic media, and so that point is fairly subtle, and so I'm not sure that I can describe it to you in words, but it is addressed in this paper, this 2018 Journal of Chemical Physics paper.
Thanks. Next one, which of the discussed models would you recommend for mimicking a crystal environment of organic semiconductors, for example, pentacene?
Funny you should ask, because I have several papers on pentacene, and it's something that we're actively thinking about. The dielectric constant that people quote for pentacene is, I think, a little less than 4, 3 point something. It is unclear, however, and there are calculations. So I happen to know the case of pentacene because my group has thought about it. And so I can tell you that there are calculations out there that attempt to take that number of 3 point something and use it as the dielectric constant. It's not entirely clear to me that that's appropriate if you're really looking at what the person is asking about, which is a crystalline crystalline pentacene. So this idea of dielectric constant is predicated on the molecules being able to tumble, right? Because for water, the difference between epsilon infinity equals 1.8 and epsilon 0 equals 78 is the tumbling of the water molecules and being able to reorient in response to charge. And in a crystal, you obviously can't do that. And so just based on basic physics, I would say that in a crystal, what you are really limited to is the optical dielectric constant, the epsilon equals infinity. Now, that being said, for a crystal of nonpolar molecules like pentacene, those two numbers are not that different, and so it may well be that it doesn't actually matter, or at least that the differences are small compared to the sort of intrinsic accuracy of these models. But if I were going to sit down and do say fragments of crystalline pentacene in continuum environment, which we actually have done in one paper recently, I would be tempted to use epsilon infinity for crystalline pentacene. If that number is known, I'm not sure that it is, but honestly, substituting some epsilon equals 3 or 4 is probably fine. This is kind of actually, I mean, I think this exposes it's a good question, and I think that the question really exposes why, the question in my answer exposes why I think it's really important to understand the underlying physics of these molecules, because if I were going to write a paper about this, if I'm planning out a calculation, I'm already thinking in my head about how I'm going to describe this to the reader, and I can articulate a rationale for why I should take epsilon equals 2 for crystalline pentacene, and I can articulate it based on the physics that I understand of these continuum approaches. And I think a lot of the users, at least whose applications papers I'm running across, much more than any other area of quantum chemistry, people want to treat implicit solvation like it's a black box where they can specify some letters and copy and paste a sentence from the user manual into their paper and not think about the details. And I think that this is not a good idea. But anyway, I don't know if that exactly answers the question, but the point is that a static dielectric constant is predicated on the molecules being able to tumble, and in a crystal, they're not doing that, obviously, but electronic polarization still exists.
Thanks. Next one, is there a way to handle embeddings transparently? For example, system-dependent exclusion volumes when setting on surfaces?
Can you say that again?
Is there a way to handle embeddings transparently? For example, the system-dependent exclusion volumes when setting up services.
System-dependent excluded volumes. I'm not exactly sure what that means, but what you can do. So when you say when I hear a term like excluded volume, I somehow, in just thinking about this picture, I somehow think about maybe there's some space that you want to be empty here. Maybe this is the best picture to use. So if you wanted to sort of manipulate the cavity around your atomistic part in order to create some sort of empty space, what you can do easily from the level of the input file is to use your own atomic radii. There's a default set of radii that come from the standard Bondi set, but those are that almost everyone uses, but or that most of the codes have implemented those. But you can specify your own atomic radii for the cavity construction, and it's described in the manual. I think it's something like $1 van der Waals section or something. But and so that would be a way, you know, if you had an idea in mind about what it was that you were trying to achieve, that you could do that. And then as long as your cavity is constructed from some kind of atom-centered spheres, then the PCM problem remains simple and has gradients. Sorry. There's an echo that appears to be related to how close I sit to my laptop. So there's a sweet spot here where it doesn't echo. So I don't know if that answers the question, but when the person says excluded volumes, that's what it makes me think about. So you can customize the cavity at the level of atom-centered spheres, and as long as the cavity is just atom-centered spheres, then all of the gradients that the manual says are available should be available, and it doesn't matter if you use the default radii or some other radii. For the PEqS model, that model was designed to be essentially infinitely customizable, but requires. But the flip side of that is that it requires you to customize, and so you know that really is designed to take an arbitrary dielectric function, permittivity function, epsilon of r in three-dimensional space, but you have to specify that, and it didn't quite make the 5.4 release for reasons of forgetfulness, but for the 5.4.1 bug fix release, there is going to be a version that allows you to do a Poisson Equation Solver calculation where you define the permittivity at every point in space. Where, let me show you one picture. It's all the way at the end. This calculation of this coumarin in octacid in water, that's how we did this calculation. Is actually, if you imagine this rectangle as just being a grid in three-dimensional space, we figured out what we wanted the permittivity to be at every point in real space, and you know, wrote a little program to generate that grid, and then read that grid into Q-Chem for use in solving Poisson's equation. And like I said, that unfortunately slipped through the cracks of we did this paper was published in 2020, so we did this work 2 years ago, but it somehow fell through the cracks of getting checked in, but it's going to get checked in for a bug fix release. But what's available right now through the PCM code is user defined radii. All right, I think I've sufficiently belabored that.
Thanks. Is the PCM model available for core ionization energy?
Could be. Trying to think. So okay, with the caveat that I haven't done it. So as per usual, there's always, you know, Q-Chem's a complicated program with infinite number of different options, and if I haven't actually done that combination of options, there's always a chance that it could fail. But I'm trying to think how it would fail, and there's no good reason. So if it does fail, it's probably something that's easily fixable in a bug fix release, because in terms of the physics, it feels like there's nothing that we're missing, right? If you're going to do that either with TDDFT, if you're going to do your core excitation, say in the gas phase, either with TDDFT or with a wave function model, you should be able to, you can put continuum on top of both of those things for valence excitations, and the formalism should work the same way. So yeah, try it out, and if you encounter problems, I or the royal we at QChem would like to hear about it because physically I think that ought to work just fine. It's gonna obviously what that's mostly for XAS, right, and not XPS, because it's gonna modify the frontier. The main effect of the continuum is going to be to modulate the frontier orbital energy levels, the LUMO and the low-lying virtual levels, and so core ionizing, probably the 1s states don't see the continuum at all, but the LUMO does, right? And so for X-ray absorption, that could potentially have an effect.
Thanks. So next question: how to obtain non-equilibrium salvation energy?
So that I'm not sure that question makes physical sense. So the whole idea of non-equilibrium is predicated on a vertical process, because, like I was saying in response to this pentacene question, the static dielectric constant is predicated on the molecules being able to tumble, right, on the the orientational averaging. And so an equilibrium PCM calculation is the appropriate thing when the molecules have complete freedom to reorganize and infinite time to do so, right? So so incidentally, by the way, and I don't have an ability to draw, but if I wanted to compute not vertical excitations, but adiabatic excitation energies, so the 0 to 0 transition, say, so the energy difference between a ground state and the minimum on the excited state potential surface, that is a calculation that you would want to do with an equilibrium PCM. And so you would do the normal ground state thing, but then you would want to optimize the geometry of your excited state molecule in continuum solvent, and that would require you to be able to yeah, I mean, that's how you would want to do that. And so this whole idea of non-equilibrium comes up only at the vertical process, because for the vertical process, the idea is that excitation is fast compared to compared to orientational motion. And so for that vertical or Franck-Condon transition, the nuclei are frozen, and so all of the orientational contributions to the solvent polarization are locked out, or they're frozen in their ground state configurations, and so your solvent polarization, in other words, is out of equilibrium with your solute, and so I'm not sure that it makes sense to do non-equilibrium polarization for an excited state, because the moment you move away from that Franck-Condon point, that the whole ansatz of separating the polarization based on the high and low frequency limits of the permittivity no longer makes sense.
Okay, thank you. We have last questions. And how would you calculate the salvation of fragments and density matrix embedding theory? That
that is a very interesting question, and the answer is I'm still thinking about it. So there's now several different approaches in QChem that are based somehow on fragments. So there's this embedding calculations, there's the Almo EDA calculations, there's also SAPT and a few other things, and I'm involved with at least with the SAPT versions of these things, and so that's an interesting question of how to apply solvent to what's the fundamentally right way to do it. And I'll tell you, well, first of all, I'm not sure. I will tell you that there is now in QChem 5.4, at least in 5.4, I think it's brand new. There is a PCM based version of Almo EDA, and the way that they do it, this comes from Martin Head Gordon's group, that the way that they do it, I believe, is one fragment at a time, and then you compute solvate one fragment at a time with PCM, and then do the Almo EDA calculations. I'm not 100% convinced that that's the physically best way to do it. What some other people do, so what the fragment molecular orbital people do, not in QChem, but I can read their papers, I believe, is when they want to do a version of Kitaura Morikuma EDA with a solvent model, they solvate the entire system in a cavity that represents the super system with continuum outside, and then internally they do all of the inter-fragment calculations with dielectric constant equals 1. And it may or may not, those two different approaches may or may not make a numerical difference, but at least physically it's that second thing that feels more correct to me, because the idea is that epsilon equals 1, or my reasoning is that epsilon equals 1 is the value that you should be using anytime that you have explicit Coulomb operators in your Hamiltonian, right? Because that's the vacuum permittivity. And so if you're really doing quantum mechanics, internally, all the Coulomb integrals are evaluated with vacuum permittivity, and so it feels like if you're trying to compute a QM interaction between two fragments, that those interactions ought to be happening through space that corresponds to epsilon equals 1. And if you solvate each fragment, if you solvate first and interact second, you're not really doing that, and you're potentially allowing dielectric medium to creep in between your molecules in a way that feels unphysical. Now, that being said, we thought about this problem a bit in the context of something like these pictures here, where I have a bunch of explicit water molecules, and we get pretty worried about possible penetration of the dielectric into regions between these explicit water molecules where in principle it shouldn't be, but in practice it's not clear that it makes that much of a numerical difference. And so I have not answered your question, but I have given you my thoughts on this. So and operationally, if you're asking me how do I actually run this in QChem, I really don't know. But I'm from the standpoint of the physics, it's something that's on my to-do list to have a student look at, but we haven't gotten around to it yet. But I've now kind of given you what my thoughts are.
Thank you, John. I think there are no more questions. I'm gonna move to close the webinar. Thank you again, John, for preparing this informative talk. If you have questions later, feel free to contact me or post your questions under the webinar thread in the QChem talk. Thank you all the attendees for listening.
Thanks, everyone.
This concludes our webinar. We also invite you to visit us on Facebook. Thank you for your participation, and see you at the next webinar.